Yeah, well, good afternoon, everyone. Questions before I get going? Okay, you'll have lots of questions after this. I'm not worried. So I'm going to talk about generic types today. Um, and so this is something that happens a lot in Scala, and for that matter in other strongly typed languages. And so when you want to work with a strongly typed language, you have to give the type for everything. And when you have things such as collections or maps here, for example, then you want to say it's a map of what? You want to specify the key and the value type in your program before you compile it. When you contrast that with working, for example, in JavaScript, where you never specify what anything is, initially, of course, in JavaScript, it's nicer. You don't have to do all of that data entry. But the trouble in JavaScript is that also the compiler can't help you. And as those of you who have done this will know, that just because your program starts and doesn't crash right away doesn't mean it does anything useful. You can later find out that what you thought was a map of strings to integers was actually a map of strings to URLs or something different, and then you mishandled it in some way and you get a runtime error. So in Java and in Scala, we want to make sure that when we define a generic type, that we say it's a type of what. So that then you have the phenomenon of type parameters. So over here we have the map type. It has two parameters, k and v. And then we can make a map of strings to integers, a map from person to person, or whatever. The problem with that is, as you will agree within the next hour or two, is if you then want to write generic operations that operate on any map, then you're going to have to specify things at a fairly high level of abstraction. So here, for example, is how you write a generic function in Scala. This function here would take the middle of a vector of any type, of a vector of t, and then we have to say, oh, getMiddle now has a type parameter. There's not just one method getMiddle. There's a getMiddle for every type t that takes as a parameter a vector of that type. And then it returns, whatever. Here we just fish the middle element. And now the compiler will infer that the return type is t. So I didn't write that here, but I could have written it. So the compiler will infer that the return type now must be the generic type t.
For this kind of use, wouldn't it be better to take a vector of any?
No. Oh, that's an excellent question. So why don't we just use a vector? I'm glad you asked. Because there's a lot of confusion about what any is good for. So let's say I would have written getMiddle not as a generic one, where a is a vector of any. And I would have written it the same way, of course, a length over 2. What's the disadvantage of getMiddle?
The return type is any.
Its return type is any. And now let's say that I have a vector of students, and I want to give the middle student a prize or whatever. And then I say getMiddle of my students, and I want to know what's their name so that I can know who to give a prize. And then this won't compile, because if the type of this thing is any has no name. And so that's the disadvantage with any type. As soon as you introduce the any type, then afterwards you lose all type information, and you can do very little with the outcome. That's why I said last time to someone, I don't know, or maybe I didn't. Did I say anything about any and why you need to be careful about any? Okay, then maybe I said it to Fatima. So whenever you find that somehow the compiler infers any, and if you did not intend that, if you did not specifically want to do something that is like super general, you probably did something wrong. So if today in the labs you find that the compiler infers any for whatever reason, you want to have a very close look at that and see if you can get rid of that any. Any is not generally very useful for for anything that's strongly typed. So that was an excellent question. Thanks very much. I should have thought of saying that. So it used to be in old-style Java, that's what one did, right? You have, that containers had objects in it, and so like what they called a vector then, or a stack, or a map, they would always work on objects, and would always have to cast, and people hated it. So that's when, with 1.2, generics were added to Java, and you had strong typing ever since. That's now a long time ago. And that was considered a real improvement in the language. Same in C++. Whenever you have to operate with void stars, it's not something that most people find a joyful experience. Right? You lose all error checking, you have to cast a lot. And so sometimes it's unavoidable, but one tries not to do that as a general strategy. So now in theory, it looks like generic types should be simple. You just put the angle bracket T in there, and then you get, when you define something, here for example I'm defining a pair. I'm saying it's a pair class, it's generic, I put the angle brackets T after the class declaration, and now what is a pair? It has a first element of type T and a second element of type T. And I just put in T where previously I might have put in string or int or something. It's just an arbitrary type. So what could be hard? And so this part is not hard. Everything else, unfortunately, is. So let's look at some of the complications that can arise. In a nutshell, the complications arise from the fact that in most practical situations, you don't want to have any old type T, but you want to enforce other constraints on the type T. If you didn't want to do that, if you were always happy to always use every type T, that would be great. But it doesn't work in a strongly typed system. So let's have an example. I now want to add some methods to this pair class. I want to add a method that gives me the smaller of the two. Now, in order to do that, I have to compare two elements. So let's say I call compare to, and if that's less than 0, then the first one is smaller. Otherwise, the second one is smaller. Now, generically, that cannot work because there's no way of ensuring that T has a compare to method. Oops, there's a typo here. It should be compare to. So first is of type T, and the compiler checks. What do I know about the type T? Does it have a compare to method? No. And so it'll reject this. So now I have to explain to the compiler, hey, I only meant T the pair of T to be formed if T is, in fact, a subtype of comparable. So I have to say, I want T to be comparable. This symbol here is what Scala uses and what's often used in type theory in general to denote subtype. So this means T is a subtype of something. I'll come to the comparable T here, why there's another T here in a minute. Ignore that for right now. But we want to say T must be comparable so that there is, in fact, a compare to method. And that's not an unreasonable thing to require. And here we require it by just specifying the constraint on T. So a reminder about types, super and subtypes. So intuitively, we say that S is a subtype of T if whenever the program expects a value of type T, for example, if it says, just to give a concrete example, var x colon T, if I can put in the thing that has type S. In that case, we'll say S is a subtype. So as an example, and I'm going to be using that example throughout the labs, we'll have a supertype person, and then we'll have a subtype student. Anytime that I want to have a person, say as a var or as a method parameter, and if I actually have a student, then a student is a person. I can use the student when the person is requested. The other way around, it doesn't work. If I have a method that expects a student, and if I give it an arbitrary person, then it's not going to work. So that's how subtypes work. So as another example of subtyping, a vector of int is a subtype of a sequence of int. So when you have a method that is willing to work with any sequence, you can give it a vector or any other sequence, like a list, for example. So generally when you have inheritance, student extends person, a vector extends sequence, then that gives rise to subtypes. There are other subtype relationships that come from something else than inheritance, but that should be your first mental model here. So a bit of notation. If one thing is a subtype of the other, then we call the other thing a supertype of S, not surprisingly. There's a little bit of subtlety with subtypes when it comes to things like built-ins. So, for example, is int a subtype of double? That would make some sense, because whenever something is willing to work with a double, you can give it an int. But in Scala, technically speaking, they say, no, int is not a subtype of double, but there's an automatic conversion. So that's a little bit different. An automatic conversion means that whenever you want to pass an int to something that expects a double, that conversion is automatically injected. Whereas a subtype means you can just pass it straight without any required conversion. So that's a minor technical issue. One could have designed a type system where int is actually a subtype of double, but that's not what they've done. So it's, at this point here, a good idea to show what the Scala type hierarchy looks like. So you will see on the left a large number of primitive types. And in Scala, they are all subtypes of a trait called anyval. That's there to distinguish primitive types from reference types. So primitive types are a little different. They copy by value, whereas reference types copy by reference. The anyref supertype here is the one that that you can use to distinguish anyvals. And there's two subtypes, two big families of subtypes. There's all the Scala classes, and then there's all the Java classes. So any Scala class extends the trait Scala object, and you can use that if for whatever reason you wanted to write some code that should work only with Scala classes but not with Java classes. I don't think it's anything that you and I will ever do, but in the compiler this happens, of course. Then, of course, there is this type any that we just talked about. Any is the everything in Scala is a subtype of any. And then there is an interesting type called nothing. And everything is a subtype of nothing. And we'll see a good use of nothing a little bit later. It's not clear right now why you would want to have nothing. It sounds so much more negative than any. Then there is the null type, which you see here. Null is a reference and not a value, and so that's why it's a subtype of anyref. The type null has a single value, namely the constant null. So that's what the type system looks like, and we're going to be needing to know that. So just to see that everyone is paying attention, how many of these statements are correct? So with the flashcards, I can't ask you which of them are correct, but we'll talk about it in a minute. But go through all of them and just count up how many of them you think are correct. So let me add a little bit of confusion to this. Remember what it means to be a subtype. So in order to decide whether null is a subtype, imagine that you have a null. And now imagine something of some arbitrary supertype. I'll call it U, for example. Say you have a variable. The question is, can you assign it null? If so, then you should agree that null is a subtype of all the other types. The same with unit. Could you assign unit to anything? All right, so let's just see some cards so I have some idea where we are. Okay. All right. Excellent. So now we have everyone's committed themselves. No one said D is. Right. All right. So is null a subtype of all Scala types? What do you say? Does anyone say yes? Okay. So since all of you say no, why not?
Because it's a subtype of all reference types.
Excellent. Because if U is not a reference type, if it's int, for example, you cannot assign it null. Right? So no. Is nothing a supertype of all Scala types? Yes, but that was from the type hierarchy, right? Is unit a subtype of all Scala type? No, that doesn't even come close, right? Unit is sitting somewhere. I don't want to flip back and lose my writing right now. It's sitting somewhere to the left with some of the other value types. So it's not a subtype of any type of the others. Is it true that an instance of any Scala type can be converted to unit? And that is in fact true, because, and you have seen that when you can make a procedure, a method, where you say def f, and then you put stuff in there, which is an abbreviation for saying this thing returns unit. And then whatever the value of this expression was, does get converted to unit. So in fact, Scala is willing to convert anything into unit, but it's not that unit is a subtype. It happens by conversion. So this one is correct, and so then two of them are actually correct. Okay. Yes.
On the previous slide, it's written that nothing is a subtype of all types. Not a supertype.
Oh. And you're right. Okay, so then I was wrong. Ah, excellent. Okay, wait. Okay, so this one was wrong. This one was wrong, because yes, very good. So we'll have another look at this and see why I was confused. This one was wrong, and this one was right. So that means anything else can be converted to nothing. It doesn't mean nothing can be converted to anything else. So that is a subtype. So the correct answer was C. Okay, moving on. What we've seen previously was what's called an upper bound. Oh, I should actually say something about upper bound and lower bound. Before we had that T was supposed to be a subtype of comparable. And so it's always confusing what it means to be an upper bound. In this case, it means an upper bound just because of the way that the less than works. And so if we look at, for example, a student, maybe person would be better. Then a person might implement comparable. And it's commonly done also that you put the the implementing class on the top. So I don't know if that's helpful in knowing that the subtype is further down. But then we did it the other way around here, right? Okay, so now I am confused. Why is the subtype on the top?
In the figure, you have put it on the top, but it's actually on the bottom.
You say I should have put it on the bottom, but hmm?
Nothing is on the bottom.
Right. Ah, yes. I see. So that is very true. Yes. Okay. Let me. I'll have to think about how to fix up the figure. Which figure do you have? Yes. Okay. So she has a better figure, where she has nothing on the bottom. So I'll need to fix my figure. All right. So now let's look at the bounds in the other direction. So here I'm looking at a pair class, and this is admittedly a little bit artificial, but I wanted to keep the example as simple as possible. And I want to have a method called replace first. What replace first does is it makes a new pair, and it replaces in that new pair the first one with whatever I put in here. So now let's say I have a pair of student, and I have a person object. I want to call students.replace first of person. So right now I have two students, and now I want to replace the first one with a person who's not a student, like me. Okay? Don't worry, it's just a theoretical example. And so what's the result? The result is now the two of us, so that's no longer a pair of students, but it sure still is a pair. It's a pair of person, because a student is still a person. So I'd like to be able to model that. And so here's how you do that. You say replace first has an extra type parameter. So this is a method inside a generic class. The generic class has type parameter t. And now I have a method that itself has a type parameter, namely r. And the constraint on r is r must be a supertype of t. So I can generate any super pair here. The parameter new first has type r. What I get back is a pair of r's, which is made out of new first and second. New first has type r, second has type t. R is a supertype of t, so the result is a pair of r. Now over here, I have written an r inside here just for to be abundantly clear. I don't have to do that. One could infer it. And oftentimes, I do omit this, although it's actually a good idea when you write this at first to put in as many type parameters as you can, just to make sure that you're doing it right. But it's not necessary. So that's called a lower bound. There's another interesting bound that turns out to be surprisingly useful, as you'll see in the lab, that is kind of similar to an upper bound, but not quite. We used comparable before, and you'll see in the lab why this was done, and also why it's not entirely satisfactory. And sometimes one wants to have bounds that work just a little smarter. And so I'll just show you what the syntax is and explain how it works, and then you'll see later why you might want to do this. So we write this thing, t:ordering, to say that the type t has somehow a way of producing an ordering. And so the reason we like to do that is that, as you'll see later, when you have a type such as int, the type int itself is not comparable, because it just isn't. The type string is comparable, but it is not ordered. And ordered is also something one likes to use in Scala. It can't be ordered because string comes from Java. So when you have these sets of types that some of them are special situations such as primitives, some of them come from Java, we don't always have complete control over what these classes actually extend or implement. And we would still like to say they are somehow ordered. And so Scala has this whole set of kind of hidden conversions, or what they call implicit conversions, that make stuff like this work. And we're not going to get into all of the details about this because it's actually quite tricky. But it's useful enough that I wanted to show it to you. So there are a whole bunch of types that can somehow summon up an ordering object that does the right thing. So as it turns out, the int type, for example, has that capability because somewhere in some file that gets looked at, and I don't want to get all the rules because they're complicated, somewhere someone has programmed in a thing that extends ordering of int and marked it as an implicit object. It has some name that doesn't actually matter. And so this is a super secret key to the compiler. If it finds one of these things at one of the right places, and it finds exactly one, I should say, then it's going to say, oh great, anytime that an int is asked to produce an ordering, I will produce this object and no other. And this exists also for dozens and dozens, if not hundreds of other types. So this gives you, as the programmer, a way of, without actually editing a class, giving it extra capabilities. You have to put these objects at the right places. As you can imagine, it sounds a little fragile and dangerous, and it is. But when it works really well. So these things exist for int and strings and for a whole bunch of other types. How do I use them as the author of a generic type? So I now want to say I have a class pair. I insist that T is one of those types that is able to procure an ordering. And then I can define the smaller method like this. I say, this is this ordering of T that I want. And then there is a magic function, a very strange magic function called implicitly. Implicitly does the lookup that uses the complex rules to find the object that you need. And this happens at compile time. So when you put this in, and later you ask for, you want to have an ordering of, say, file, then it will not compile. But once we have it, we get back this ordering object, we have our compare method, we can call it, and then we can make decisions on this. So this is actually quite powerful, and this is the modern Scala way. So this Scala uses what's called these type classes, these classes of behavior more and more, and when you arrange your stuff, it actually does make the code pretty simple. All right, so we'll go on to the first lab. I thought I had another clicker question, but nope, you luck out. So in the lab, with these labs, you have to be kind of super careful what you're doing and in which order you're doing it, and you're very likely going to get confused. In that case, raise your hands and ask, because these things are subtle. Sometimes you look at something and it looks like it's correct. What I would always recommend you do is that you mouse over the various types and see that you really get what you need. If ever that nasty three-letter word, any, appears without your wanting it or without me saying that's what you're after, then let me know and I'll have a look and see what's been going on. All right, so let's just do it. Yeah, it's a bit of a long lab, so we'll probably need all the time that we can get.